Today I'm going to talk most of all about proton NMR relaxation, and you probably haven't heard very much about this. It's a quite new technique, so there's not many people able to look at it, but it gives us a very good picture of the cement paste because you can do it without any drying out, and you can do it like in situ and repetitively on the same sample. So it's really a very powerful technique. And thanks to this technique, we then went back and compared with MIP, and actually we can see that mercury intrusion porosymmetry is actually very good for characterizing porosity. It's been much maligned in the past. People say it's no good and it doesn't measure anything. But if you do it properly, I now think it is a good technique. And finally, I'll say a few words on SEM, which, as I've already said in the previous lecture, is pretty useless in terms of quantification. It's great in terms of seeing the porosity, but it's quite useless to quantify it. So NMR is this really unique technique, and it uses water as the probe. So it's called proton, and proton are basically the nucleus of a hydrogen atom. So the hydrogen atoms you have in water, and you can use those to probe the porosity. So you don't need to dry. In fact, the opposite. The pores need to contain water, and you can make many in situ measurements on the same sample. And these are some of the key publications we've written on this technique. Most importantly, I mean, this technique's been around for a long time. We really review those techniques in this paper here. So we go back over the whole history, which is about 40 years of the use of this technique. What I think has been the big breakthrough we've made, which I'll explain to you, is that now we can really be sure we quantify everything. Before, according to the different instrumentations, people maybe measured part of the water, but then we couldn't be sure what part they're measuring. So how does it work? Well, the idea is quite simple. In detail, the equations governing it are quite complicated, but you have protons, which are hydrogen atoms, and they have a spin. And then you apply a magnetic field, all the spins line up. Okay? And then you remove the magnetic field, and it goes back to the random orientations. And the time for this going back to random orientations, which is called relaxation, depends on the size of the pore. So if I have water in this beaker here, this is in a very large container, and the relaxation of this water will be about 4 seconds. If I have a small pore, then the relaxation is much faster, because as this water molecule is going around in this pore, it will sooner or later hit the surface, and when it hits the surface, it immediately relaxes. So the higher the surface to volume ratio is, so the smaller the pore, the faster will be the relaxation time. So the principle is quite simple. The details are quite complicated. It does go into that in the chapter, but you don't really need that to appreciate what you can find out from proton NMR. And then if you have water bound in a crystalline structure, this has a very fast relaxation time because it's not mobile. Now, the kind of equipment you need to do this is really quite small. This is the equipment in our lab. It's this little machine here. So it's not, some of you may have seen NMR equipment, which is these, huge magnets for solid state measurement. It's not like that. And it's quite sort of reasonable cost in terms of research equipment. It's of the order of 50,000 euros kind of cost. And you see, it's just, the magnetic field is not all that strong, so you don't have to take special precautions or anything like that. And there's a sort of hole in the top of this sample, and into your hole you have a tube. You put cement paste in the bottom of this tube, and then we usually put it in a glass cylinder so we don't have massive amount of airspace, and then we seal it all very carefully. It's very important that you seal it very tightly. And you can keep measuring this sample as long as you like. and we've measured up to 300 days, up to about a year, but you could go on longer if you wanted to. So I'm not going to go into the physics of the signal acquisition. It's described in the book. It is quite complicated, and you do need to work with somebody who understands it to understand how to do it. And as with many of these techniques, it's best applied to pace because aggregate dilutes the signal. So the two methods for those of you who want to know the technical terms are what's called quadrature solid echo and the so-called CPMG spin echo sequence. So these are described in the book, but as I said, we don't need to worry. But there's two sequences of applying magnetic fields and removing them that you get the signal. And the first thing, as I said, which is very important, is we now know that we can measure all the water. And we can do that by an experiment like this. So this is the normalized signal, and this is the normalized sample map. So these samples have been prepared in different relative humidities. And you see, as the mass is lost from the sample, then the signal goes down into one-to-one correlation. And for these conditions of drying in relatively mild relative humidity, you see the solid signal is not changed at all. So then we have this spectrum, and this time it really is a spectrum, and you see this spectrum shows you the different populations. So if we look at the mature sample, 62 days, we can see 4 distinct populations. This population here, this one here, this one here, this one here. And you can see how they evolve over time. So fairly quickly, this signal here, well, very quickly, immediately, this crystalline signal is in exactly the same place. Then this one, and then these are the pore sizes. As we go to the left, we're going to smaller pore sizes. So this first signal here, we're very confident that this is the water in the crystalline hydrates. In this case of a white cement, the only crystalline hydrates we have are calcium hydroxide and ettringite. And we can be very sure of that because these numbers for the amount of water here match very, very closely with the calculations we can make from X-ray diffraction. You know, we can measure how much calcium hydroxide there is by X-ray diffraction, calculate the water in it, and the numbers agree almost perfectly. So then, logically, if this is the solid water, the water in the crystalline hydrates, the next population, which is this population here, is the interlayer water in the CSH. Okay? And this is very interesting because many people have said water in CSH is exactly the same as crystalline water, but it isn't. We can see that the relaxation time is about 10 times slower, which means the water is more able to move about. It acts like it's in a pore of a slit pore of about 1 nanometer. And 1 nanometer makes good sense because with CSH is like tobermorite. It has a layer spacing of about 1.4 nanometers, but a lot of that is taken up by the silicates and the calcium. So the space for the water is about 1 nanometer. And then this next population here is the gel water. And we see it's got a characteristic size. And then finally, we come to the capillary water. And usually we see actually there's 2 populations of capillary water. And what's also very important is that the amount of water in the capillaries is actually very small. Now, these are sealed samples, so that's quite explainable. But even though you've got quite large capillaries in sealed samples, as soon as you have setting, because of this chemical shrinkage we've talked about, the larger pores become voids. They become empty of water because the total amount total volume goes down, and so the overall volume of the sample is staying fixed, and therefore we have to create voids. So, yeah, we see these 2 populations, and I'm going to come back to that point there. Now, so that's really what I've just summarized here. So those are the 4 populations we have. Now, the capillary porosity has 2 distinct populations, and the shortest one stabilized to a definite size after a few days. And for reasons I'm going to explain, we call that interhydrate porosity. So let's look at these capillary pores. So this shows us how the signal of the capillary pores evolves in time. And here we see the sizes, the average size of the capillary pores. And you can see the average size of the capillary pores, which still contain water, goes down very, very dramatically, so that even after 1 day, it's only 10 nanometers. This is quite surprising to most people because they think you can still see large pores. That's true, but those large pores don't have water in them. They're the voids that are created by this chemical shrinkage. And after a certain time, you find that the size of these pores doesn't decrease anymore. It stays at a fixed number. So the amount decreases, but the size doesn't. And we think this size, this 8 nanometer size, now corresponds to these spaces between these CSH needles. So this is a transmission electron micrograph, and you can see these CSH needles we saw quite a lot of in the microscopy lecture, and then these narrow spaces between them are about 8 nanometers. So after only a few days, the water in the pores is all in these very small pores. That's really why I want to emphasize that SEM is really so useless as a technique for understanding porosity. And here's another TEM picture of a LC3 paste. You can see how dense it is. Nearly all the space is filled by these needles of CSH, and the water or any other infiltrating species like chloride has to go through these narrow spaces. And we can actually see the same thing by mercury intrusion porosymmetry. I'm going to speak more about that in the second half of the lecture, but we can see the same thing. This pore entry size becomes smaller and smaller, and then after a certain point it stops. So that was the capillary population. So now we want to look at the other populations, and here's the population of the interlayer water. So this is our kind of model for CSH, that we have these sheet structures with water in between, and we have regions in which these sheets are well stacked and organized, and then these sheets sort of bridge from one organized region to another. So this interlayer water is the water between these sheets. And then we have the water in the gel pores, and this is what we think of the gel pores. The gel pores are these more open regions in the CSH. And at the beginning of the hydration, these 2 signals evolve in proportion to each other. That's to say, as we form the CSH, we're also forming the gel pores. The gel pores are an intrinsic part of the CSH. But after a certain time, and it's actually the same time as we find that the capillary pores stop getting smaller, we see that we get no more gel pores formed. The gel pores just stay level. So this really shows us that there's these 2 modes of growth of CSH. First of all, CSH is growing by these needles, and then once these needles have kind of more or less filled up all the available space, then we have to form CSH either as this dense inner product or by densifying these needles. And we see we form no more gel pores. So the ratio of gel pores to interhydrate will change as a function of time. And we can take all this information and we can make some very interesting calculations. For example, we can calculate the density of the CSH in situ, and this is the only technique that can really do this calculation of CSH density. It has also been done by small angular neutron scattering, but that's an incredibly complicated technique you can only do with a synchrotron. This is a technique you can do in more or less any lab that has this equipment. And you see now we have to look at 2 different types of density. We can talk about what we call the solid density, which is the density of these well-organized regions of CSH, which is just the calcium oxide silicate layers and the water in between. And you see the density of that part is really very constant, which is what you'd expect. But the density of the bulk, that's to say the well-organized regions plus the gel pores, is increasing over time. And it's really just increasing over time because after a certain time, the CSH that forms doesn't have any more gel pores. And we can see that, in fact, these values we get for mature samples of about 2, this now agrees very, very well with all other estimations that have been made from other techniques. We can go further. We can calculate the amount of water in the CSH. And again, we can see that for the solid part, we have a quite constant amount of water, which is about 1.8 water molecules per silicon atom. And then in the bulk, the amount of water is going down. And here we come down to a value of about 4, which again agrees very, very well with what you can read in the literature as the assumed value of CSH calculated by other techniques. So it's really a very, very rich technique that can give us an awful lot of information. We can even calculate the calcium silicate ratio. We can see that this slightly is decreasing in this sample from 1.8 to 1.6. So with all of this information, this can lead us to actually updating the famous diagram from Powers. So most of you will see this Powers diagram. Now Powers took cement. He then took the hydrates as one. He didn't differentiate between CSH and calcium hydroxide and ettringite. And then he said there was gel water and capillary water. And the values we have here for a mature paste agree very, very well with the values that Powers calculated from his data. The big change is that Powers just do straight lines for all these interfaces here, and we can see we have straight lines in this case, but in this case, for the boundary between the gel water and the capillary water, we don't have a straight line, we have a curved line, because the gel pores form early, and then they stop forming, and after a certain time, then we only have the capillary pores or these interhydrate pores. There's still more information we can get from this NMR technique. So this shows us what happens to the NMR signal as we do this desorption and absorption. So this is done in a standard equipment where you equilibrate your cement paste to different relative humidities, and then after the different times, the NMR signal was carried out. So the red population here is the crystalline water, and we see the crystalline water stays pretty constant right down to relatively low relative humidities. This is now the interlayer water. So the interlayer water you see is not affected until we get down to pretty low relative humidities. This is the relative humidity scale up here. So after we get down to about 27% relative humidity, then the water comes out of the interlayer. And this is the gel water here. So the gel water progressively empties and is empty at about 30–40% relative humidity. Now the capillary pores are on this because right almost at the beginning of the experiment, when you've hardly gone below 100, you're still in the 90s, then the capillary pores appear not to contain any water. So this is all information we can get to that, and we can describe that information in this kind of diagram which shows the state of the CSH at different states of relative humidity. And we've used this now quite extensively. We've used it for white cement, for grey cement, with additions of silica fume, additions of metakaolin. In all of those cases, we see basically the same thing. CSH is all basically similar. It has a similar density, even though we can have changes in the calcium to silicon ratio. We've studied effects of temperature. We were talking about this earlier. When you increase the temperature, you increase the density of the CSH, and that explains why for samples cured at higher temperatures, the long-term strengths are not as good as curing at lower temperatures. So the main limitation of this technique is you do need to have samples with a relatively low iron content. Iron really interferes with the signal processing with the magnetic field because it's a magnetic material, and it just destroys the resolution of your measurements. So that's why most of the studies are done on white cement, because that has a very low iron content, and you can get very good resolution of signals. Most grey cements are not too bad, but you can't get such fine resolution. And then with these additives, silica, fume, and metakaolin, these don't contain iron, so you're okay. But you can have, and you can also do it with slag, but fly ash is more of a problem because fly ash often contains significant amounts of iron, and that will cause you problems. So that's the NMR technique. And with this information, we can now go back to the mercury intrusion porosity technique, which is much more widely available in many, many laboratories. And, you know, this technique was, 10 years ago, people said this was a rubbish technique. It was completely unreliable. I think we've got to completely revise this point of view, and we've published this in a paper recently. So it does give you good results if you prepare the samples correctly. And the main problem for most of the results in the literature is that people did dry at 105. And we've gone on about this all day. 105 drying completely destroys your microstructure. It creates huge, great cracks. And then with the mercury intrusion porosity, all you measure is cracks. And that's not really what you want to measure. And if you interpret it correctly. So one of the main criticisms that's been made about mercury intrusion porosity is that you have what's called this ink bottle effect. So the idea of this ink bottle effect is shown schematically here, so that, here you're intruding the pores of this size, and then you increase the pressure and you intrude the pores of that size. But the problem down here is because that pore there is connected by a narrower pore, it doesn't get filled. And it's only when you get down to that narrow size that then you fill all this pore here. So all this pore here is measured as being of that size. So that is undoubtedly a problem, but as we will see, because of what is really the dominance of these interhydrate pores, the problem of the ink bottle size has really been overestimated. Now that same effect can be seen kind of more graphically in terms of a kind of model structure for a real cement in these diagrams here. So this is just a two-dimensional simulation where you can imagine the pore space is this white space between these black dots. And as we increase the pressure, then the mercury, model mercury, can intrude through smaller and smaller gaps. And you see there's a kind of threshold where suddenly it really starts to penetrate a lot of the sample. So, a lot of these pores in the middle of the sample, which are really quite large, get measured as pores of a smaller size. And, these effects are undoubtedly there, but not as dominant as we once thought. Drying, as I keep saying, is the big problem. And this compares the effect of different drying methods. So these are mercury intrusion porosity curves for white cement, the same white cement we studied by the NMR technique. And we looked at solvent exchange, vacuum drying, freeze drying, and then oven drying. And you see even oven drying at 50 degrees is really pretty damaging. And 105, well, it's not actually much different. You've done the damage even at 50. You've created the cracks, which just give you this much earlier onset of the mercury intrusion and much higher total porosity. So by far the best technique is solvent exchange. And this is best in terms of the fact that the mercury doesn't start to intrude until the latest time, and then we get the smallest porosity measured. So what are we measuring? Well, in this case of this white cement, you can see you get this kind of first intrusion here, then it kind of levels off, and then it goes up again. You don't actually see this last bit where it goes up again in many materials. You do in this white cement for reasons we don't quite understand, but in grey cement you don't really see it. And we think in this case, this is the intrusion of the capillary pores up to here, and then when you get this very steep slope again, this can be going into some of the gel pores. But I stress the word some, because it's only a very, very small amount of the gel pores that the mercury gets into. So in this study, what we did was we took the curves and we said, okay, this last part we think is going into the CSH gel, so we're going to ignore that, and we're going to look at the correspondence between the capillary pores we measure here and what we measure by NMR. Now in NMR, I explained that we can only measure pores with water in. And we saw in these sealed samples that we only had a very few capillary pores with water in after a certain time. So with NMR, we also have to add in all the void space, and the void space we can calculate if we know the chemical shrinkage. So we did all that. And here in these plots, what you see is NMR, the capillary by NMR, plus the void space, calculated from chemical shrinkage, and then MIP capillary pores. And here for a range of water cement ratios, 0.3, 0.4, 0.5, you can see it all agrees very, very closely. We didn't get quite such good agreement for the underwater cured, but we think there's a good reason for that, because we had quite different sample sizes in the two cases. And because it's difficult for water to get into all the pores, we think we might have had sort of different things in the two cases. But here we can see another curve where we're following these quantities over time, and you really see how really well they agree. So I think there's no doubt that if you treat the MIP curves correctly, and you look at the pore structure that's included right down to if you see an upturn, which you may not see, or you can take an arbitrary cutoff at 10 nanometers. That also works fine. Then this really does correspond to the real quantity of capillaries and voids in the system. And now if we compare the whole measurements, what are we really measuring? So, you know, this is what we measure by MIP. We measure the void space. We measured the blue capillary pores and a little bit of this gel porosity. But you can see it's very far off from being the whole gel porosity. So you really should subtract off this last part here, because this is unreliable. Sometimes it's a large amount, sometimes it's a small amount. And we don't know the reasons for that. And in fact, we can then use this to back calculate the so-called density of CSH, because we know how much CSH we have. We know how much porosity we have, and we can see the densities all agree very, very well with what we had from NMR. So summarizing all that, the comparison between proton NMR and MIP shows that MIP is a good characterization technique. It measured the voids and the capillary pores, and after a few days, really all the accessible pores have to be accessed through these interhydrates. And with that taken into account, the ink bottle effect is not as important as people have imagined. So what else can we see now by MIP? Well, I said in NMR we saw that the pores went down to a certain size and then stopped. And we can see this very much by MIP as well. So this is just plain cement paste. This is plain cement paste at 0.4 water cement ratio. And you see now by about 14 days, the porosity's got down to a certain minimum size, and then it doesn't decrease anymore. The amount decreases, but the size doesn't decrease. If we have the same Portland cement with quartz, however, I mean, this would be the same as making a much higher water cement ratio. This would be the same as going up to a water cement ratio of about 0.7. Then the porosity can't get down to that minimum pore size. It stays much larger. So we can see similar things with fly ash if we cure it underwater. If we give it enough water, then eventually will take longer, it will get down to similar critical pore sizes. And also with slag, we'll go down to similar pore sizes. And as we reduce that pore size, when we reach this critical pore size, then we change the degree of reaction of the fly ash. So you see the fly ash is reacting quite fast here, but after about 20 days, when we've reached this critical pore size, then the rate of reaction of the fly ash completely slows down. So all these things, the cement paste, the fly ash, etc., are all being limited by what's happening after we reach this critical pore size. And here we can see, again, with slag, we can see that by difference between the quartz reaction and the slag reaction, this difference here is the slag reaction. You see here for 0.4 water-cement ratio, it starts reacting fairly fast and then it tails off. If we've got a higher water-cement ratio, then the slag can react more. So the reaction of all these phases is controlled by space. And all this was summarized in a paper we published with Borodier, which showed how all these things are coming down to the same critical pore size. And what we think is happening is this. So if you imagine a crystal growing in a simulated pore space, once it'll fill up the bigger pores, and then to keep growing, it has to go into pores of smaller and smaller size. And to grow into that pore of smaller size, this curvature of the crystal has to increase. And as the curvature of the crystal increases, then the supersaturation of the solution needs to keep increasing for the crystal to keep growing. So this is all well known in the theory of crystal growth, that the higher the curvature, the higher the energy of the surface, and then the higher the concentrations you need in the solution to keep growth growing. So what we think is that after a certain time, the pores are so small, and you can't anymore get this classic growth of hydrates into small pores. You have to go to other mechanisms which we think are densification of the CSH. So that's really what I've summarized here. So just to finish this, as I said, what about SEM? So there's this very famous paper by Diamond in CCR, where he compared what he got by image analysis to what they got by MIP. So there's a number of points on this. First of all, if you look at the MIP, you see this breakthrough diameter here was about 100 nanometers, whereas we are now seeing breakthrough diameters of about 10 nanometers. So I didn't check, but I think he almost certainly dried the samples at 105, so that's a problem. And then we see this image analysis data, which supposedly starts measuring pores at 10 micrometers. So, and then the resolution was only 1 micrometer, so they couldn't measure anything below that. But if you now look at a picture from a well-prepared paste, this is a well-prepared paste. Where are the pores which are 10 nanometers in that sample? You know, I can't see any pores of 10 nanometers. About the biggest pore I can see here is this little one here, which is what, about, 1 or 2 nanometers, micrometers, 1 or 2 micrometers. So I'm not sure how he was able to get such big pores by image analysis, but I think we have to ask a lot of questions about how we prepare our samples. And to illustrate that, here are 2 pictures. So this picture I took in my thesis in 1984, and it was done with a paste with a water-cement ratio of 0.5. I hand mixed it, and this is at 24 hours, and it was freeze-dried. And it looks like there's this huge amount of porosity. And this sample here was made by Patrick Guillaume in his thesis in 2009. It was done with a very high mixing speed. It was solvent exchanged, and you know, the electron microscopes have improved somewhat, so you know, I think the contrast was maybe rather high here, and because the contrast is high, there probably was some product in this space we didn't see. So I think this just really illustrates the problem of SEM. You know, it depends on the contrast settings. If you have your contrast set too high, you can black out a lot of stuff as pores, which isn't really pores. If you don't mix your sample properly, then you don't form the hydrates throughout space, as really does happen in a proper concrete. So these are all things you have to be very careful of, and why I wouldn't use SEM to quantify porosity, although it's very good for a lot of things.